Well, we're back here at the 2023 Northeast Astronomy Forum, or what's called NEAF. I'm here with Norman Fullum from Optiques Fullum, and Norman has been an incredible force in making beautiful telescopes, and also large aperture telescopes. And you know, a lot of people think that, well, large aperture, what does that mean? 20 inch, 24 inch?
Well, 20 years ago, yes. 20 inches was a big telescope.
It was a big telescope, right?
When I first made my first telescope, was a 12.5 inch, almost 30 years ago, and that was humongous.
Right.
For amateur astronomers.
Sure.
12
you were
and a half
probably in the
inch.
upper 1% of.
Oh yeah, I was going to Star Party and I had a lineup behind my telescope.
Sure.
Hey, he's got a 12 inch.
Holy smokes.
Now, time changed.
Time has changed. So I think that today you're making a folded Newtonian design. We could let's talk a little bit about that advantage of a folded Newtonian.
So the reason why I started these folded Newtonian is I'm a visual observer myself. Okay, I love imaging and looking at pictures.
Sure.
But visual for me is my thing. So, and of course, when you have a Newtonian design, the larger the diameter of the mirror, the higher the eyepiece is. So that's a very drawback unless you do the f3 or even larger than 30 inches diameter mirror. Even if you do f4, the eyepiece still at 8, 9, 10 feet high up in the air.
Right, I've seen guys climb ladders getting up to
so
bigger
if you have a
telescopes.
40 inch or 50 inch mirror, f3.5, the eyepiece would, the eyepiece would be at about 15 feet high up.
Guys should have a crane to pick you up and put you
in
up.
the wind. It's very, very scary, and it's not safe.
It's not safe. You're right. It's not
safe. And you fall off a ladder at night, and I mean,
you could easily die.
Yeah.
Right.
And if you fall on a mirror, then you break the mirror, and it's not fun. Anyway.
And then you still die because you're having a heart attack. Okay, so
because you broke a mirror.
That's right. Okay.
So I started to think about design to lower the eyepiece. So I designed I call it the Fullum folded Newtonian.
Yeah.
So it's just a matter of lowering down the secondary mirror and change the angle to get the light cone and the focus point out of the structure halfway down.
Okay, so on a regular Newtonian, you got the primary
you go
mirror,
up like this,
and then you got a 45-degree angle.
brings the light
eyepiece is
sideways.
sticking out.
Yeah.
Isaac Newton came up with this idea, right?
Exactly. Hundreds of years ago.
Right.
Still working.
Still working.
Yeah. So
But
now
you've
I
got that
change the
mirror.
angle.
Okay.
So the cone, instead of going like this, goes downwards like this.
Okay.
So if the structure ends here, you manage to get the focus point out of the structure, and you put the focuser there.
Okay.
Different angle, different way to observe. But I mean, like I said,
Is it comfortable though? I mean, having kind of.
Well, there's two ways to do it. You can either use just a straight pipe focuser with the eyepiece, then you have to look, when you're at the zenith, you have to look up like this or sideways, depending on the angle.
All right.
Or you can put just a coude in the focuser.
Like a diagonal. Okay.
Put the eyepiece in the diagonal, and then you can twist it around.
Oh, that would make it very comfortable.
A comfortable way to observe instead of having the.
Instead of trying to figure out a way to rotate the tube, but
exactly.
A big telescope, you can't do that.
You can't do that. No.
Okay. All right.
So there's two ways to use it. Most of my customers use a coude. So anywhere you can point the telescope at, you change the angle of the eyepiece, and you're comfortable to observe. And most of the time, you have the 2 feet on the ground. Even for a 40 inches or 45 inches telescope.
Wow.
50 inches, you can go up maybe to 8 feet high up at the zenith. So if you look at,
so you might have to get on like a step
maybe
stool.
one step stool instead of being 15 feet high up.
Yeah.
So
so you won't need a parachute on your back to, in case things go wrong.
The thing is that most some of my customers for those large telescopes or research group, not research group, but they do outreach for people or educational or tourism also.
Right.
So
and astrotourism is at all-time high right now.
And if let's say someone buys a telescope like this and wants to do some promotion and do some tourism, insurance doesn't like you to go up the ladder at 15 feet high up.
No.
They won't do it.
Right.
So if you can have a telescope that even the kids or the older people, the handicapped people can get to the eyepiece safely,
Right.
a couple feet off the ground, they like it.
Wow, so you've really thought this through. Now,
Yes.
to be honest with you, up until I saw your folded Newtonian design, I'd not seen folded Newtonians. Is this a new idea that?
I've seen it in the past at cellophane. Some people have tried smaller versions.
Okay, all right.
But never the way that I do it. But I think it's innovative idea,
Absolutely.
and I think it's a proper, like the one that I built for a Mégantic observatory in Quebec. Okay, it's a professional observatory, but also I have astrolab for astrotourism. They had a 24 inches cast grain there, very powerful telescope, but they wanted something bigger for the tourists and public and education also. So they look at my design, and because of my design, they decided to go with a 36 inch. Otherwise, they would have stayed with a small telescope.
Right.
Well, not small, but smaller telescope.
Right.
So that gives access to very large aperture optics telescopes.
Okay, so we got to talk about the experience of very large aperture. Okay,
Yes.
now everybody knows that if you're into astronomy, you know more aperture is going to give you greater resolution, much brighter images of everything you're looking for. This makes it easy to find stuff,
Exactly.
too, right?
Yes. Yes.
You know, instead of having to be a highly trained deep sky observer,
and
right?
then you see a little smudge there, and it could be it, but I'm not sure.
Yeah,
When those large aperture, I mean, poof, the object is there.
So
And
something like Stephen's quintet.
Oh man,
Obvious, right?
Obvious, yes.
Obvious, not just like a hint. Like I think that's Stephen's quintet there.
No.
So
textures are much nicer, depth of object. If you look at the globular cluster with a 50-inch telescope,
oh my God,
I mean, it's like swimming in the pool of stars. You go through. It's unbelievable the effect that you have,
right?
And especially if you use binocular.
Right. Wow. And you've used binocular.
Yeah, on a 50-inch. Yeah.
That would just look like super 3D.
I think my best memory of looking through a 50-inch telescope with a binocular, looking at M42.
Okay.
Orion Nebula.
Color? Colors.
Colors all
Not
over the place.
color, but color.
Colors.
Okay.
And the 3D effect of depth of the nebula itself.
You were using a binocular to look at this?
Yeah. I
Smokes.
could have stayed at the eyepiece for hours.
Right.
And see different things, and it's like mesmerizing. So
I get mesmerized looking at the Orion Nebula. I can't imagine that kind of view. And I have used larger telescopes and observatories, never with bino viewers. Okay. I've used like the 60-inch Mount Wilson. But you know, you're above Pasadena with this telescope. And it's amazing, but you know, you're kind of sitting there as an amateur astronomer going, wow, I wish I was under really dark skies. And with a telescope like what you build, it can be transported.
Yeah, well, some of that
not super portable, but
they can be movable. Movable.
Okay.
I have me and my consultant engineer, we designed a portable 50 inches telescope into a mobile observatory.
Wow, 50 inch.
50-inch folded Newtonian that you don't have to carry off the trailer. The trailer is the observatory.
I see.
So you get on site, open up the trailer, jacket on hydraulic
It's like a clamshell or something?
clamshell, the telescope, you isolate from the ground. And you're on site with a 50-inch wherever you go.
Dang.
That's amazing. Those are projects in the near future.
Can you imagine being like out in Utah or Bryce Canyon or Big Bend National Park or the Texas Star Party or any place where it's really super dark?
Exactly. So that's a big advantage of shorter telescope, but you're not limited by the diameters, the aperture. Yeah,
but okay, you got a big aperture telescope. Wouldn't that like take all night to cool down? I mean, right?
I thought about that.
I know the answer for this already, but I wanted to give him a nice lead in for this because it really is amazing the way that this guy designs optics.
Okay. About 10 years ago, I had that dilemma. Okay. Customers were asking for larger optics, larger mirror, and what was available on the market was solid borosilicate blanks. And as soon as I got larger than, let's say, 24 inches or 30 inches diameters, they got so heavy And most of the time you have problem because they keep them very thin relatively to this diameter at 2.5 inch, but still 2.5
That's a
inch
lot
thick.
of glass.
Lots of glass. They never get into thermal equilibrium at night. So we did the test.
Right.
It's
So you
never-
couldn't have a.
So the mirror, you got aperture, but the poor image. So what's the dilemma? What do? We want thinner mirror, faster cooling, but if you have an inch mirror thick, the mirror gets so fragile, it deforms itself under its own weight, so you have astigmatism. That's another drawback. The image is
Absolutely. Yeah.
So-
I mean, why would you want to? You get this big aperture. You're expecting a beautiful, perfect star image, right?
and then it's all over the
Yeah.
place.
Right.
So I contacted the optical department of Laval University in Quebec,
Okay.
and I talked to the guy that wasn't some kind of amateur astronomer also, and then he understood my problem. He said, let's work on that problem. So I said, I give you a goal. My goal is to have large aperture, lightweight,
Yeah.
fast cooling, and cheap.
Wow. None of those things go together, actually. So,
never.
right?
So we worked almost 3 years together to
Okay.
do that. I acquired a big kiln, and
Kiln.
a kiln, a big
Yeah.
oven
Yep.
to be able to melt and fuse the glass together. And we came up with the design. We call it. No. That's the camera.
We're actually live here. And to prove it,
It's
somebody
all right.
put their hand over
It's
the
all
camera.
right.
That's cool. It's cool.
So
Yeah, that's right. You can blame. I won't. I'll just give out his initials. Larry Weatherly. Okay.
yeah, that's him.
Anyways.
So where was I? Okay, so what we did is that we use borosilicate, which is Pyrex.
Okay.
And a few shot company sells them in sheets, huge sheets.
Sheets.
Sheets
Okay.
of different thickness.
Okay.
So the way to be able to cut those big sheets, we thought about laser, but laser is not good because it induces heat, induce stress in the glass. It's not good. So we thought about water jetting, water jet cut.
Yeah, I've seen water
Perfect.
jet on
Yeah.
metal.
Yeah.
It cuts glass.
So it's glass like butter.
Wow.
So we ordered some disc, different diameters.
Okay.
The first one was a 36 inch. Okay. 36 inch plate. Okay.
All right.
We cut 3 plates, 36 inches, and then some strips, an inch and a half wide, the length of the sheet.
Okay.
So we took the first 2 sheets of 36 inches, put them together and fuse them together in the kiln
Melting.
to
them.
make them about an inch thick all together.
Okay.
Okay. After that, what we did is we cut those strips, all the same size, same length, and we
So like
computerized.
pylons or something.
Pylon, and we use a computer program to make sure each pylon is at the right place to get the most rigidity out of the blank of the mirror
Okay.
itself.
So it doesn't.
So there's a pattern.
warp or bend.
It's not anywhere.
Okay.
We have a pattern that we put a dot wherever each of them goes.
Okay.
So, but in the past, a few companies had tried to do that similar type of approach.
Okay.
But they had a problem of print through. When you do the correction, print through,
And
when
when-
in the figure of the mirror, everywhere where there's a post was fused,
Sure.
there was a bump.
Oh, you could actually see the.
You can't see this visually, but if you
Okay.
test it, you see that.
Oh, you'll
there's a
see
bump.
it.
You'll see it right there. So we've managed to find a way to fuse the 2 posts, the 2 ends of the post to the top and the bottom plates with an interface that melts at a lower temperature than
Oh,
the
I
rest.
see. Okay.
I won't tell you what it is.
That's fine. I don't want you to give away all your secrets,
so-
so.
We tried that.
It's
It's
interesting
about
to know.
50 micron thick, very thin interface on both sides.
Okay.
And we arranged all the posts on the bottom, which is the bottom plate.
Okay.
Put all the posts and put the top plates on the top and put that in a kiln.
So it's a sandwich.
It's a sandwich. Yeah.
Okay.
Put it in a kiln and fuse it together.
Okay.
Our worry was that maybe the fusion wasn't very good or whatever. So we did some tests, and each post, when at the fusion point, okay, we took a weight of 30 pounds, okay, break it apart from the plate, okay, the test.
Okay.
And it took 30 pounds to break it.
Okay.
And half of the top plate came off at the same time than the post.
Oh, wow.
So
okay.
it's really
It's really
melted and
attached.
to it. It's not just stuck to it. It's stuck.
Okay.
It's not like
Okay.
it's glued together.
Right.
So
And
we
if you have a
knew-
number of these things, this mirror must be very strong.
Let's say on a 36 inch, you have about 150 posts.
Wow.
So it's solid. It's like a solid blank.
Yeah.
Okay, when it's fused together.
Okay.
About a fifth of the weight, less than that. I think it's a seventh of a weight.
Okay.
As an example, a 6 inches thick, 36-inch mirror Techno-Fusion weighed about 140 pounds only.
Wow.
Versus a solid mirror,
Hundreds of pounds.
thousands of pounds.
Thousands of
If it
pounds.
was a solid.
Yeah.
Okay.
Wow. Okay.
So we gained we reduced the weight, that's for sure.
Yeah. Okay.
Then we want.
Well, this has got to be a safety factor right there.
Yeah.
You know, that you've got something you can manage
Yeah.
safely because
Exactly.
you drop something
The
that
manipulation
weighs
is done by
thousands
suction
of
cup.
pounds.
Suction cup, just move it
Okay.
around from
All right.
on the keel to the machine. So now we have a blank parallel back and front. Okay, only an inch thick at the top.
Okay.
And if you want to do a 36-inch f3.5, there's not enough material in the center to grind it.
I see.
Okay, so
How did you solve that?
Okay, so I thought about it. Why not slump the entire mirror to the F ratio?
The back and the front, everything.
Yeah. So I got a company that makes convex mold that goes in a kiln.
Okay.
Okay, some kind of a ceramic that it's machined to an F ratio that I need.
Okay.
Take the mirror
Upside down.
the front stays on the mold. Heat up the mirror enough that it can
brilliant.
soften the glass. And
That is
whoop,
brilliant.
and it takes a shape.
Yeah.
So you got a convex back with a little bump because of the column itself at the back.
Yeah.
But the front, flip it over, you got an inch thick front plate
Man.
with the approximate F ratio that you need.
Okay. So on a
Put it out on a
traditional
grinder.
mirror, you would be like grinding.
Grinding.
And that would take all that time.
take
and-
months.
Right, and expense.
Expense, yes,
Right.
exactly.
Right.
So that takes to make a blank of 36 inch, it has to go 3 times in the oven. And every time the glass has to be annealed properly. So it's about a week at a time to reach
So
fusion
you
or
bring up
slumping.
the
And then it takes
temperature.
about a week to cool down very, very slowly.
Gravity's taking over to
Yeah.
bring it down.
Yeah. And then when it's done, the temperature has to go down a certain amount of degree per hour. So there's no stress induced in the cooling time. It's called annealing the glass itself.
Right.
So at the end, you end up with a lightweight mirror. Because of the internal structure, mechanically, the blank is about 5 times more rigid than a solid one.
Wow.
And on top of that, because the top plate is only an inch thick, it takes about 20 minutes to cool down with the proper ventilation.
20 minutes.
To
Okay.
We did the test with
My refractors take longer than 20 minutes to cool down.
yeah, because it's enclosed.
Yeah.
There's no air movement
Yeah.
inside.
Yeah, yeah.
My mirror in the telescope, I was thinking about it before I was making this. That if I have airflow in between the top and bottom plates
Right.
all the time, the mirror would get into thermal equilibrium. just like
Really
that. And it
fast.
works because on one side of the telescope, I have air blowing, and
Yeah.
the other side, air take it out. So you always have an airflow.
So on your telescopes, you probably have
The same
fans
thing.
that are pulling the air
exactly,
across.
pushing
Okay.
and pulling.
Okay.
And we did the test with the thermal
20
with the
minutes.
thermal camera,
Uh-huh.
and we filmed it. We took a blank of 12-inch, 2 and 8 inches, the normal 12-inch in the past that we use for mirror blanks,
Uh-huh.
and we put a 40-inch mirror Techno-Fusion next to it from inside the shop at 25 degrees Celsius.
Mm-hmm.
It was winter time. We took them both on a table outside in the winter in Canada. It was about minus
Cold.
15 Celsius.
Yeah, it's cold.
Yeah, they put a fan
Okay.
on both of them.
Okay.
Okay, and we put a camera, took a film. Within about 20 minutes, the thermal fusion was in all the same color.
Wow.
The 12 inches at about 2 inches around the mirror that was in thermal equilibrium.
Wasn't
The rest
done
was
yet.
hot again. Still.
Oh, man.
So it shows us that it works.
Yeah.
We can get a very large mirror into thermal equilibrium quick lightweight, and the bonus on that, borosilicate is cheaper than zero-dur or any exotic glass.
Right.
So it brings down the price.
Right.
Manufacturing.
So just to give some idea about this, so let's say that we were to go and buy a regular, like a classic 50-inch mirror, okay, versus a techno-fusion mirror. What kind of, have you done that cost analysis? I mean, is it
I'm probably
100 times more or 10 times? I don't know.
It's minimum 10 times more.
Okay.
Minimum.
Right.
And if you can get a proper blank.
Right.
Because it's pretty hard to find those blanks. You have to have them made. And the big drawback on having a big blank made, they have to melt material and end up with bubble in it. So when you do the grinding, figuring, you already have bubble.
So you're grinding it and you see like these bubble pits.
Yeah, there'll be bubble holes on the surface.
Wow.
Yeah.
After spending all that money and
exactly.
Right?
Yeah.
Okay. Wow. All right. So
versus the borosilicate sheets, they call it, it's rolled, they all rolled. So they melt the borosilicate and they rolled it on a melted tin, and there's no bubble in it.
I was at the Pyrex Museum, or not the Pyrex Museum, the
Corning.
Corning Museum in Corning, New York.
Okay.
And they showed that process where they flow the glass on top of
melted
metal. I didn't know if it was tin.
Yeah.
But it was fascinating to watch it. So that's how it's made.
But the blank for mirror, they're melted in the mold. So they take borosilicate, Pyrex, chunks, put it in a mold, and then heat it up so it melts and it's loose. But there's always bubbles in it.
Right.
Because it melts in between.
Yeah. So if you go to Mount Wilson Observatory and you take the tour of the 100-inch, they always show the mirror, and it's made out of wine bottle glass. So it's green, but you see bubbles all over through it.
All over. Yes.
Yeah. Yes. Right.
So if you, let's say you grind and polish, and then there's a bubble popping out, you got a hole in the mirror. It's not very important because it's a hole. You lose a little bit of light there. But if you got 20, 25 little bubble hole on the 40-inch, and you got some little scratch there, because it's normal on the large optics to have a little sleek there and there, because material that we use to polish is not 100% pure. There's always a little scratches there.
So I'll add something here. Most amateur astronomers would freak if they saw scratches and sleeks and bubble holes in their mirror. I mean,
but it's just cosmetic. Aesthetic.
Of course. I mean, that's that make telescopes. We know that that doesn't affect performance
at all.
But
it's visual.
Look, you're an amateur astronomer. If you're watching this program, you probably are. How careful do you look at the mirrors on your telescope? Okay, you probably look really hard at them. And in the amateur astronomy telescope manufacturing community, we work real hard to make that beautiful. Okay, it's not a performance thing; it's a beauty thing. And most amateur astronomers won't believe you.
No, they won't.
They won't believe you. They say, "Oh, I see the sleek. I see the."
But what's important is the parabola, the shape of the mirror, the figure itself.
That's right.
That's what is important.
So you have solved also a cosmetic problem.
Cosmetic.
So your techno-fusion mirror is going to look
the
more
risk
beautiful.
Of bubble hole. That's just about eliminated. The bubble hole.
Okay.
So here I am. I have a product. Now I have to convince people that it's working for that cheap price.
Right. Because they go, no way does this work that well.
And the thing is that I cannot approach any company or individuals or groups with that because they don't have the funding. So I have to find someone. First, I have deep pockets. Inspired by what I do and wants to try it. And I found a few customers and it works. And then I developed the folder Newtonian because now
somebody had to take a leap of faith, right?
Yes.
Okay, all right.
So now I had the optics.
Now, how far back are we talking? How many years ago?
10 years ago.
10 years ago. Okay.
Now I have a viable mirror, large mirror, and now, but I didn't want to have the first. Well, those first mirror, you remember Orion Telescope Company?
I do. Sure.
they approached me because they heard about that.
Yeah,
said,
they
"We
wanted
want
to
do
sell the biggest telescopes.
monster scope."
Monster scope, yes.
But it was a regular Newtonian.
They were really long,
yeah,
right?
I had even brought here one at NEAF.
I
one
remember
year,
seeing it, sure.
and they're great, but they're so dangerous to observe with.
Yeah.
You were at 12 feet off the ground.
Yeah.
So we never sold any. Never. I sold one.
Sold
the
one.
prototype to a group in Quebec, in northern Quebec. They bought
Okay.
and they use it. They love it. They have a secure ladder that they built around it so they can observe securely.
Okay.
But otherwise, the idea wasn't good. For me, it wasn't good.
Okay.
I said, I need something lower. How do I do it? And then I created the folded Newtonian. That's how we managed
That's
it.
awesome.
That's how I came up with that. So I had a diameter, large aperture telescope, not too expensive because of the primary mirror. I managed to make a structure not too expensive either, made of aluminum, composite. And now we're starting to add some 3D printed parts to it that we do ourselves.
Sure.
So it's evolving. It's constant involvement.
Okay, and it's on a Dobsonian style now, right?
Yeah, it's like a altitude azimuth movement,
Okay,
all motorized, go to. It's all go to.
All right.
So you just sit down and enjoy. It's
Without having to climb a ladder in the middle of the night, you know.
Exactly.
I think personally I would be a little apprehensive to climb up the ladder in the middle of the night by myself, okay,
I've done it many times.
right, by myself.
Excuse me.
I've used big telescopes like that too, but there's always somebody there, you know, we kind of spot each other, that kind of thing, you know, hold the ladder. But if you're going to be observing by yourself, much rather be doing it with 2 feet on the ground, right?
Exactly.
Okay, so that's that. Now let's talk a little bit. I mean, usually a big telescope takes years to make. I mean, somebody ordering a big telescope from you, what's your turnaround time?
Depending on the diameters, it's anywhere from 10 months to about 14 months.
That's
maximum.
lightning fast.
Yeah, because I do the structure at the same time that I do the mirror.
Okay.
Everything's done parallel. I have 2 sides of my shop, one for the optics, one for the mechanical parts. And when I start the mirror, start the structure at the same time. So everything evolves pretty much at the same.
Okay.
And then when I get to the point that the mirror is finished, the structure is just about done. We do the first assembling without coating the mirror, because I do coating also in my shop.
Right.
So we assemble the telescope with the mirror in it to balance the entire structure, make sure that everything is well balanced. Then we take it apart, coat the mirror, the primary mirror, secondary mirror.
Okay.
And then we reassemble it, do a start test, and
Check
make
all
sure.
that.
It's hard to do the start test at the shop because there's so much light pollution, but at least to know that the focus point is at the right place, make sure. Double check.
Right.
Then it's all taken apart, and have a private company that comes to the shop and do measurement.
Okay.
They build the crates
All right.
that I need to ship it wherever on the planet.
Okay.
So
Wow, well, that's impressive. I mean, you saw so many things about a big telescope, and I know all of us that are into amateur astronomy, we dream about having something like this. I mean, still, it's not cheap.
No,
okay,
no.
but
if you compare, if you just compare,
you compare and look at what it costs to get any other telescope in this aperture class, it would cost
there's
millions of dollars.
But there's no suppliers right now for amateur astronomers or groups of a club other than for astro imaging or research group. If you don't have visual, you have some kind of a testing apparatus at the focus point.
Sure.
You don't look through it. Right. So I'm pretty much the only one making it available for visual viewing.
Okay.
For large aperture.
But what about astrophotography? I mean,
no problem. Now the technology is so advanced, and I have a couple of friends like Hugo. You met Hugo, I think, online.
Hugo, I did.
He's a maniac of imaging, okay? And he developed a program to do very short exposure. Okay.
And that's what most amateur astronomers are doing today.
Yeah. So now you put the camera at the images, you put the camera at the focuser, and you do the imaging. That's it. It's all motorized. It's got to go to, and it's tracking.
You could operate it remotely, probably, right?
Yeah, exactly. There's no
Wow.
there's no reason why you couldn't do imaging with it.
Okay.
So,
Okay.
I'm
All
not
right.
an imager. I'm a visual guy. But
Right.
if you want to do it, nothing stops you.
Okay. So we have put into on this show, you'll see the link where you can go and look at a 40-inch optique Fullum, a folded Newtonian, and you know, you can see the price of it and everything. But I think that you talked about possibly there might be some 50-inch telescopes that you might be able to find at a deal. So
Yes.
right.
There's, one of my first customers had ordered a 50-inch. He has it for the last, I don't know, 6 years, 7 years. And he changed hobbies. So it's a very wealthy person, and he has many hobbies, and then now he's into sailing. So he's got this nice observatory in the desert in California with a 50-inch there. It hasn't been used, I think, the last 2 years. And
So that may be available.
that could be available for a very good price.
Okay.
Contact Scott
Yeah.
about it if
Right.
you're interested to have
Sure.
more details. I will contact the owner eventually in the short period and
Okay.
see if it's something that would be
Well, that would be exciting to
Yeah,
get that telescope back in service.
Yeah, because
so
you see, you have a 50 inches not in service for the last, I don't know, many years.
right.
And how many club would love to have that?
Oh
And,
my
I mean,
gosh.
it's like a dream come true.
I mean, if I had something like that, you know, and I was living out where it's dark,
Yeah.
I would definitely flip the switch and make an astrotourism program out of that
Exactly.
for outreach, and
Yeah.
also just, you know, for the income stream that would
Yeah,
come from
yeah.
something like that.
Yes,
You know,
yes,
so, right?
yes, absolutely.
Okay,
Uh-huh.
so we talked about the folded design, you know, how they keeps you from getting the double chin
Yeah.
from looking, you know, the wrong
Yeah.
way into a telescope.
Yeah.
And
Like talk to Karim about that.
okay, and got just so many positive aspects of that. You know, we know this isn't for everybody, but it could. It's within the realm. It's within the realm of possibility.
Compared to 20 years ago,
Yeah.
that wasn't available. Now it's available on
Yes,
the market. So
right.
I think it's something interesting for many people
Sure,
and realistic for less people, but still it's there.
it's there.
It wasn't there before.
Right.
Now it's there.
All right. Well, Norman, thank you very much.
Thank you very much for having me at NEAF this
Yeah,
year,
yeah,
inviting
thanks
me
for
to
coming
have
and
my little corner on your table.
Talking to everybody
And,
here.
Talk
so,
to people about my dream.
yeah.
And we'll see you soon.
Okay. All right. Well,
Thank
thank you. Thanks. Okay. So we're here live from the 2023 Northeast Astronomy Forum here in Suffern, New York. We've got more speakers coming. So stay tuned and thanks for watching this one. And take care. Keep looking up.